Okay, we're now recording, so over to you.
Right, good evening and welcome to another CAS webinar. I hope everyone is still keeping safe and well. The next CAS webinar is on the 24th of August, when we have Professor Chris Lintott's presentation on Crowd and the Cosmos. This is based on his book of the same name. There are 45 names on the reserved list for that meeting, and I will email each one with the link the week beforehand. Tonight we have Eddie Carpenter giving us another anniversary 2-minute talk on one of his fellow countryman astronomers. Then we have Mary McIntyre, whose presentation is on reflection, refraction and excitation, the hunt for atmospheric optics. So let's give Eddie a warm CAS welcome for his talk.
Oops, sorry.
Okay, thank you. I think I might cheat a little bit on this one. A discovery, if you look at European astronomy books, they put this discovery down to on August the 11th. But I'm convinced that it was made actually in Arizona, the west coast of America, and over there it would have been August the 10th. Well, that's what I'm hoping anyway. Well, that's what I'm going to do for the anniversary. August the 10th, 1877. Anyone any idea what it might be? Well, there's a chap at the Naval Observatory called Asaph Hall. Asaph Hall. And he discovered Deimos, the small moon of Mars.
All right.
And then 6 nights later, he discovered the bigger moon of Mars, Phobos. The mystery is, why did he discover the faint, small one first? You think it would have been the bigger, bright one, wouldn't you? Mm. And I've come up with 2 ideas, which might be wrong, or you might have some ideas. Was Phobos, when he was looking around, perhaps behind Mars or in front of Mars? Or was it simply too close to Mars? And Mars can be quite bright. And if you've got a moon very close to Mars, it's a devil of a job to see. These are 2 moons I've actually failed to see. I've tried cutting out the glow from Mars, but at the moment I've been unable to discover Deimos or Phobos. Anyway, that was the anniversary I'm putting down to August the 10th, 1877. Asaph Hall discovered Deimos, the smallest moon of Mars. I got a phone call this afternoon from the Bristol Astronomical Society, and someone else found another one, an anniversary for August the 10th. I'm not sure what date I'm not sure what date it was. I did write it down, but I forgot. It was the foundation stone laid for Greenwich Observatory. Don't know if anyone knows that date. Foundation stone laid for Greenwich Observatory, August the 10th. I've lost the date. I've got so many bits of paper here. So that was another anniversary. Anyway, the other thing I was going to do perhaps occasionally is talk about Cornish astronomers, people from my own country. And the most famous one is, so who do you reckon the most famous Cornish astronomer was? Anyone any idea? No. John Couch Adams. That's it, John Couch Adams. He was born on the 6th of June, 1819, in a farm, a little farm called Lidcote Farm, in the poky little village of Lan East, just 2 or 3 miles southwest of Lanson in North Cornwall. Very big family, lost count of the number of brothers and sisters, all very intelligent, all with their heads screwed on right. They all became scientists or doctors or priests. But he was a genius at maths, apparently. And at the age of 10, he probably could have actually passed an A-level maths examination. He was actually teaching other teachers mathematics. Anyway, he entered St. John's College in Cambridge in 1839, studying mainly maths with some astronomy. And he came up with the idea that there must be a planet further out than Uranus. He discovered the orbit of Uranus, and it was doing funny things, being disturbed by something. People thought it was Saturn, but no. He was convinced it was a bigger planet further out than Uranus. And he sent his findings to his tutor, James Chalice. Challis didn't seem any interested at all in it. Probably thought, oh, some student coming up with some bright idea. Just didn't bother at all. He actually took it up also with John Herschel. And John Herschel wasn't that interested. He then took it actually to the Astronomer Royal. The Astronomer Royal at the time was George Airy, but he wasn't available for it. You say he had other things to do at the moment, but he'll look into it later on. I think a bit of a dirty trick was done on John Couch Adams, because Airy did actually tell Challis sometime a few days later to have a look. And Challis did look and did spot something. He spotted a blue dot, which he thought might be this undiscovered planet. Made a note of it, but obviously had to wait. So I'll wait until tomorrow night or the night after and see if I can check it and see if it's moved. But he just didn't bother at all. There he was with a bit of paper with his dot marked on it. That was the new planet, going to be Neptune, but he didn't actually go back on it to double check it. Meanwhile, back in France, another mathematical astronomer, Leverrier, took over and got contact with John Couch Adams. They actually had a big powwow about it. And he thought, yes, I think you're probably right, John. And he sent the coordinates to Germany, to two astronomers, Gale, I'm not sure how you pronounce it, Galle, and one of his assistants called D'Arrest. And they, without wasting time, got onto the great big super duper refractor telescope. The story goes that Gale was on a stepladder looking through the telescope, and D'Arrest was looking at a star map. And the star map in Germany in those days was far more accurate than an English star map. And Gale was saying things such as, I can see in the eyepiece a bright star up at the 11 o'clock position, magnitude 4, and D'Arrest would say, yes, I can see that on the star map. I can see a double star near the center, very faint stars, magnitude 8 or 9. And D'Arrest would say, yes, I can see that. And then you say, oh, look, at 3 o'clock, there's another bright star, magnitude perhaps 3. Yes, D'Arrest was saying, I can see that. And then he said, down at the 5 o'clock position, I can see another star, a bluish star. And D'Arrest said, no, it's not on my star map. He said that, D'Arrest said, that dot that you've seen, particularly as it's a bluish dot, must be the planet. So the story goes that, was it D'Arrest who actually spotted Neptune or Gale? And most German books put it down as both of them, Gale and D'Arrest. French books often put it down as Leverrier. And English books often put it down as John Couch Adams was the main discoverer. So it's a shame really about Challis, otherwise he would have gone to England. I don't think John Couch Adams was very pleased with Airy, because I said Airy probably told Challis to have a look behind John Couch Adams' back. Airy actually offered his job of Astronomer Royal to Adams, but Adams actually, I think, was so fed up, he said, no, I don't want the job. So anyway, that was just a little bit about probably the most famous Cornish astronomer, John Couch Adams, born the 6th of June, 1819. If you go to Cornwall and you go to the town, market town of Lanson, there's a lovely museum there where they've got a room with a lot of John Couch Adams ephemera there, his books, his notes, some of the instruments used. He wasn't an astronomer, he didn't actually have telescopes. He did have a few other instruments, but a lot of the ephemera and information on John Couch Adams is in Lanson Museum. So if you're ever down in Cornwall, I know it's a long way for you, but it's well worth spending half an hour in that room looking at some of the documents they have there. And there's nice, easy, free parking outside. I did it a couple of years ago. Okay, then, anyone, any queries, anything, any questions, comments?
That was very interesting.
Thank you.
Yeah.
Very interesting.
Yeah.
I've got one of Adams's books, mathematical books, and you can't read it. It's just solid math. It looks like it's written in Martian, but no, he was a mathematical astronomer, but should have had the praise, I think, a bit more than he did.
Aye.
Okay, then. Thank you.
Thank you. Thank you very much, Eddie. That was great. Right. So, Mary has loved astronomy since she was a young child, a love that stemmed from her mum. She is also a keen astrophotographer and has had her images published in astronomy magazines, astronomy books, local and national newspapers, and on various TV shows. She also loves sketching astronomy objects. She has also had articles published in the Sky at Night and All About Space magazines and a couple of books. In March 2018, she was elected a Fellow of the Royal Astronomical Society and is a member of the BAA, the SPA, and the Society for the History of Astronomy. Mary also plays bass guitar and sings with local musicians. So please give Mary our usual warm CAS welcome.
Thank you. I will just do the screen share. So this topic tonight is probably something that's a little bit different from the stuff you've had before. Some people say that it isn't astronomy. I disagree. I think it very much is part of astronomy. And it's a part of astronomy that I knew very little about until I moved to Oxfordshire and had a bit more sky visible to me from the back garden. I'm just going to, is it Alt-M to mute? Oh, it's
Sorry, yes, Alt-M.
Alt-M, thank you. I can never remember the shortcuts. Yeah, so atmospheric, obviously I was aware of rainbows, and we all are, although we probably don't understand the complexity involved with rainbows, and I will go into that a little bit. But also I'm going to spend quite a bit of time talking about some of the more common ice kind of crystal effects that you might see. The advantage of atmospheric optics is that very often you can do it in the daytime, so you're not up late. It's usually a lot warmer, so you're not having to stay out in the freezing cold for hours and hours. And it's just really good fun. And our word of caution, if you are looking for stuff that's around the sun, please protect your eyes. Make sure you put your hand up and block the sun out before you try and look at any of the effects that are on the sun side of the sky. A lot of the stuff I'm going to talk to you about is on the other side of the sky as well. And I'm just going to go through them in turn, and hopefully you'll learn a little bit of something. Now, we are all astronomers. And as astronomers, we're used to kind of setting up our telescopes and cameras, and then clouds appear, and then rain comes, and then we end up flooded, and it's a nightmare. And this happens time after time after time in the UK. But I hope by the end of tonight that you'll realise not all clouds are horrible. We are supposed to hate clouds, but when you can get effects as beautiful as this, then they're very much worth observing as well. And in the UK, we have a lot of cloud, and there's not a lot we can do about that. And I've just found it very interesting to learn more about clouds, because it's something that we see pretty much daily. So kind of embrace it and learn about it. The title of my talk includes excitation, so I'm going to talk about aurora. And my talk is kind of talking about my experience of aurora from mid-latitudes. You guys are further north than me, so some of the stuff is still relevant, and probably more so, but there are certain aspects of it that will be slightly more difficult for me than they are for you. So I'm going to talk about that. And in amongst all of this, I'm including noctilucent clouds as well. So it's going to cover a lot. I'll try not to overrun too much, because this is one of those topics that the more I read about it, the more interesting it gets. Now, the scientific principles that underpin all of the atmospheric optical effects that we see are reflection, refraction, dispersion, and excitation. A lot of them are one of these things. Rainbows, for example, are a mixture of all of them. And I'll just briefly run through the differences between those things. Now, refraction, if you ever look at a pencil in a glass of water, you can see that the pencil looks different in the water than it does above it. Refraction is where wavelengths of light, because all these things that we're seeing are down to changes in wavelengths in light, because they're from the sun or the moon. It's basically what's going on. If the light waves hit a barrier and change, kind of go into a cloud or into an ice crystal or something like that, what happens is that the wavelength changes. It will change direction, but also the crucial thing is that the wavelength of light will change, and that is what gives rise to some of the effects that we see. And so that is the main thing that makes refraction different from diffraction. Diffraction, things kind of move around an obstacle. Now that obstacle could be through or around a raindrop, it could be through a gap in the clouds, it could be through a hole between a series of mist, but basically diffraction will mean that the waves of light get kind of spread out, or they change direction, or something happens to them, but the wavelengths of light stay the same. They don't go through the same wavelength change that refraction does. Reflection is something we're familiar with because we all have mirrors. If things were all just a straight plate of mirror, then it would be very easy to explain. But when you're talking about, for example, raindrops, which I'm going to be talking about in detail with rainbows, if you're talking about internal reflections from a sphere, this is one path, this is another path, and then there are all the paths in between. So I've got an animation that shows this better in the rainbow section, but there are so many different things that can happen within a raindrop simultaneously that give rise to some of these effects. So reflection, this is what we're talking about here, but also the secondary rainbow that you get will be a mirror image of the first. So there's a lot of complexity going on there. You can also get reflected rainbows that kind of shoot up in a straight line out to the side of a secondary bow. That is reflected off a lake or a body of water. So that's what's going on with reflection. And dispersion, we all know because of Pink Floyd. Obviously, any of us that did physics at school will be familiar with the prism, and sunlight goes in, it gets refracted twice by the kind of faces of whatever prism you're putting there, and then when it comes out the other side, it's dispersed into its constituent colors. Now, a lot of the stuff I'm talking about tonight is around hexagonal shaped ice crystals, so the path isn't quite the same as through one of these prisms. It's going in here and gets refracted, then when it comes out, it gets refracted again, and because this first refraction has happened at a different angle, very slightly different angle because of different component parts, that change happens again at the other side, so then you end up with a form of dispersion. You don't get the same sort of dispersion that you get in a rainbow in this sort of crystal, but there are certain atmospheric optical effects that do have a full kind of rainbow prism effect. So that's mostly what's going on with the ice crystal stuff. It's all hexagonal shaped stuff, but there are other shapes as well that I'll talk about when we get to that part. The final bit of the talk is about excitation. If any of you remember physics, you'll know that electrons kind of exist in these shells around the outside of the atom. When a stimulus comes in here, it will send an electron from the ground state up to an excited state, and it could go to this one or this one or this one, it doesn't really matter. But it's not stable there. So when it falls back down again, what happens is a photon of light is then emitted, energy is emitted. And this is exactly what is going on with aurora. So I'll refresh this when we get to the aurora part. So that is the excitation part of the talk. So that is all the science done. The rest of it now is just kind of pretty pictures and information. Little caveat here, I've mostly used my own pictures here, not for self-promotion, but because we don't often get these amazing multiple halo displays in the UK. We just don't get the conditions for it. There are pictures that I'm using that aren't mine that do demonstrate this, but a lot of the pictures I'm showing you because it gives you an idea of what to look for in the UK. Most of the things I'm talking about I have seen in the UK. I photographed them, just never at the same time, which is incredibly infuriating, but I have seen them all. So the pictures I'm showing you are my own, mostly to give you a realistic idea of what to expect when you are looking for these effects. So first of all, rainbows. These are the things. Rainbows, it's quite interesting. Everybody knows what a rainbow is. Very few people understand what's going on with a rainbow. But because people know what a rainbow is, whenever people email me saying, oh, I saw this little rainbow, but it was pointing the wrong way, it's because it wasn't a rainbow. All atmospheric optical effects get labeled as a rainbow, even when they're just not. And it kind of drives me a bit mad. So I try to be patient and explain to people it is not, in fact, a rainbow. And it is just one of those things. And rainbows are very, very interesting. There's a lot of stuff I learned about rainbows when I was putting this talk together. Very often you do get a secondary bow. They're much fainter and the colors are in reverse order, as I mentioned before. Almost always there is a secondary bow, but because it's a lot fainter, it often goes unnoticed. And what's really interesting about rainbows as well is that each time you get one, it can look completely different from another time. And even within one bow, I've seen parts where the rainbow is fatter than another part, and it's all down to water droplet size. So it's really difficult to actually get a good idea of what causes what type of rainbow, because you don't even know if the person standing next to you is seeing the same thing that you are. And so it's really difficult. The only way you can really analyze rainbows is to just look at how you are seeing them and make your own measurements of them. But each kind of color spectrum, it's not a defined edge. It goes through in a kind of analog way. There's no definite boundary between the 7 colors that we're all brought up to believe are in rainbows. And what one person sees isn't necessarily what another person sees. I do think they're very interesting though. Now, rainbows from any one location are not as common as you might think. And the one that people refer to the most, but from any one location, you may get less than 10 a year. And that'll come as a surprise because we're all on social media these days, and almost everywhere there'll be a rainbow somewhere in the country. But you have to have the sun below a certain angle, an altitude, otherwise a rainbow can't form. You need the rain to be kind of illuminated by the sun. You need the weather front to be moving the right way, otherwise the rain stops before the sun comes out again. So they're actually not as common from any one given location as you might think. That said, last month we seem to have a lot, but generally you don't get anywhere near as many rainbows as you do the other optical effects. These are caused by a combination of refraction, reflection, and dispersion, and there's also some quantum mechanics going on in rainbows. There's some crazy geometry going on that is actually very difficult to explain. Now, you may have noticed sometimes if you ever do observe a double rainbow, or a primary and secondary bow, the center of the rainbow is brighter than the band in between the two, the primary and the secondary, and that's the Alexander dark bow. And it's basically because the photons of light are being focused within this cone of light, and therefore the middle of the rainbow is actually fully illuminated. You don't always see that, but you quite often do. Now, if you was looking at a rainbow from the side, you wouldn't be able to see it. It is not a fixed object in space, and that's really important to understand, that your rainbow is those water droplets and light rays focusing on your iris, your retina. And the person next to you has got their version of it. So you are not guaranteed to be seeing the same thing as each other. It is not a fixed object in space. So it's quite a difficult thing to get your head around, but it's easier to think of it as a cone of light. If you was above the horizon, a rainbow would be a full circle, and we generally see part of it. Now, the angle of the sun's rays off these water droplets is always somewhere between 40 and 42 degrees. The center of a rainbow is the anti-solar point, which is the point directly opposite the sun. So if the sun is high in the sky, obviously the anti-solar point is well below the horizon. So if the sun is above 42 degrees in altitude, you cannot see a rainbow. If it's a little bit below that, like right on the cusp, you may just see the top of a rainbow. So rainbows look very different with differing sun altitudes. And that it's quite an important thing to remember about different optical effects, is how they can be changed by the sun angle. This was taken by me from the field directly behind our house. This is a very flat looking rainbow here. The sun was at 35 degrees, so not that much lower than it is for a rainbow to even be visible from a flat horizon. So that was taken at about 4:45 in the afternoon. This rainbow was taken when the sun was only 3 degrees up, and it's then you've got almost the semicircle here. Obviously, if I was up high, this would be the full circle, but assuming we're on a flat horizon, the anti-solar point is only just below the horizon here, and you get that really high arch. Now, this one was when the sun was 0.3 degrees above the horizon. This is when the rainbow pretty much turns red. This is not just me playing with the color contrast here. This is actually what happens. The rainbow becomes red for the same reason that everything else goes red during sunrise and sunset. So those colors become very much more red. The reds in the rainbow stand out more. And actually the red parts of the rainbow, some parts of it can remain visible for about 10 minutes after sunset. At this point here, this is the lowest sun altitude that I've ever seen a rainbow. It was extremely faint, but it's really interesting to just compare the shapes of them. Now, if we look at that bit there and zoom right in on it, you can see that it looks like it's a straight line. And just the other day, somebody in the Atmospheric Optics and Halo Spotters group on Facebook posted a picture saying, I've just seen a flat rainbow. That is also a name given to a different atmospheric optical effect that I'll talk about in a minute. And it's really important when you have seen something to make sure you communicate the time of day, the sun altitude, and where the sun is in relation to the picture. Because if you've just taken a quick phone picture and the sun isn't in the field of view, it's really difficult for people to try and help you identify what you're seeing. To actually see a completely flat bow, you need conditions to be perfect at exactly the right time, and they are pretty spectacular when you do see them, but they are not a flat rainbow. You are just seeing the very top bit of a curved thing. So I like to make the joke about don't tell the Flat Rainbow Society that their rainbow is actually curved. But yeah, if you zoom in on just the top part of it, it will look flat, but it isn't. You're just seeing the very, very top of a sphere. That's why it looks different. And the full circle rainbow was something that had only been speculated until observations from the air, or this was actually taken from the top of a tall building in Perth, and you can see that it's a full circle. I've also seen drone footage as well. Somebody did a drone photograph from the side of a waterfall, and there was a waterfall rainbow, full circle, primary and secondary bow, absolutely beautiful. So the anti-solar point here would be bang in the middle there. So yeah, if you're high up, you will see more than just the semicircle that we're kind of used to seeing. But it's not just the semicircle, the whole thing is a cone of light that is focusing on your eyeball. So your rainbow is your personal rainbow, and nobody else will ever see it the way that you just did. So I find that quite special. Now, I mentioned before that there are lots of different ray paths through the rainbow. These graphics that I've made for this talk were created using atoptics.co.uk, which is an excellent resource for all of these things. Generally, anything that has a variation, you've got a slider down the side here to drag your mouse around to show how things change. And I've basically just created an animation by screenshotting the different mouse positions. So that's how I've created these things. But you can see here the light entering here can come out in any number of different places, and this is what gives rise to the dispersion and the different colors and the primary and the secondary bows, and also the supernumerary bows that you can sometimes get as well. The supernumeraries, very often you get them when the rainbow is very bright, and they're also associated with very small raindrops. This picture kind of makes me sick as a dog because it was taken during our eclipse trip 2017 in the States, and we're being on a day trip to my favorite place on earth, and I knew I'd cry when we left because I love that place so much and I didn't want to leave. So I said I'd drive back, and I'd never driven on an American road before, but I just thought I've got to drive back from Breckenridge, otherwise I'm going to cry the entire 2-hour journey back to Denver. As we were driving down a 4-laned interstate, one of the brightest rainbows with the most number of supernumeraries I've ever seen happened, and I couldn't get a picture of it because I was driving, and I was absolutely hopping mad that I'd insisted that I drive. But I took my husband's picture and I processed it myself, and you can see that these supernumerary bows just keep going to beyond the reach of what we could see with our eyes, and sometimes you can get many of them, and they tend to be pink and green with a bit of blue in there. These are the things that we know that they're associated with really small raindrops, very fine rain. So sometimes they can appear and disappear during a rainbow's visibility. But the actual geometry of how this forms in a spherical raindrop doesn't actually make any sense. So there is a quantum mechanical effect here. It's hypothesized that quantum mechanics is at work in order for supernumeraries to form. So I think that's awesome. I know absolutely nothing about quantum mechanics. I'm a doofus when it comes to anything mathematical, but I love the fact that parts of a rainbow may be quantum mechanics, because rainbows I do know something about. And very often, if you are taking a picture of a rainbow, there will be raindrops falling down in front of the camera. And this is something that I was not aware of until my friend Pete Glastonbury posted this picture. If you look at this raindrop here, you can see that there is a color spectrum within the actual raindrop as it has fallen. which is amazing. So now whenever I'm taking pictures of rainbows, I'm looking at the individual raindrops to see if I'm seeing something like that myself. You obviously need not a super fast exposure to get this, but I just love the fact that there's a spectrum within a single raindrop as well as the rainbow. It's just so beautiful. So there's always something new to look for. Pretty much everything I'm talking about tonight that you see in association with the sun, you can also get a fainter version in association with the moon. A moonbow is it's generally not as colourful as this, certainly not to the naked eye, but obviously the camera will pick up colour more. But you pretty much need a full moon in order for one to form, because otherwise there just isn't enough light. Giuseppe Petrica is an amazing guy. I follow him on Twitter. His photography is amazing. I think he lives up in the far north of Scotland somewhere. He's got aurora and a moonbow. That's just showing off. I have never actually yet seen a moonbow myself, because although I do like spending a lot of time outside when it's clear at night, unless there's a thunderstorm, if it's raining at night, I'm generally inside doing something. I don't tend to stand outside in the dark in the rain. But yeah, they are beautiful, and you will have all the same things. The moon being at different heights will affect the height of the rainbow, but it will always be around a full moon that you might get one. So yeah, if it is full moon time and the showers, then definitely something worth looking out for. You can also get something called a fog bow. You may also get them in mist and fog, and they just form this really pale, colourless arch. The top of this is kind of missing. It was barely even misty. It wasn't a particularly strong mist, but I was just out in the car and I could see something, so I stopped and took a picture, and that was the brightest fog bow that I've ever seen. Paul Money took this one when he was up in the North Pole. I think he'd gone on an eclipse trip with Sky at Night, and he got this incredible fog bow. Again, they are caused by water droplets, but they tend to be suspended in the air, and they're much, much smaller water droplets. Therefore, the colour isn't really apparent in them. They tend to be white. There's a hint of colour in this one, and you do, if they're bright, you can sometimes get a hint of colour. You may also get them forming on dew as well. If you're out in a field that's completely covered in dew, you can get something called a dew bow, and they are low to the ground. But your mind kind of tricks you. Your brain will see it as a hyperbolic shape, even though it is technically circular, but it's flat on the ground. This is something else that I've never seen, mainly because I don't do dawn. I never get up early unless I've stayed up all night. I don't see dawn usually. Terrible at mornings, always have been. So I'm not normally up in time to see the dew. But if you are an early riser or you go walking your dog, then it's something else definitely worth looking for. And that again is just tiny water droplets. And if they're suspended within spider webs and that kind of thing, then you can get that effect as well. Now, while we're on the anti-solar side of the sky, I wanted to draw your attention to anti-crepuscular rays, because they often go unnoticed. This is one of the favourite pictures that I've ever taken. It's quite an old picture now, taken with my Galaxy S5 mobile phone, but I was out because there was this rainbow and I noticed these bright rays kind of pointing out to it. But obviously there's a rainbow here, so the sun was behind me on the opposite side of the sky. And this was the first time I've been aware of the fact that you can get rays on the opposite side of the sky from the sun. Now, crepuscular rays, they're called crepuscular from the Latin crepusculum, meaning twilight, and it's a bit misleading because these guys are visible anytime that there is sun and cloud. So they happen pretty much daily because there's always at least one cloud visible. And if I was running a book on the atmospheric optical effect that has caused me to nearly crash my car the most number of times, it would be crepuscular rays, because they can be really striking and I'm constantly glancing to see, oh my God, I need to pull over and get a picture of them. They're always changing, they're visible all the time. Sometimes you get little punch holes through clouds and they're just beautiful. If you see these, you're almost guaranteed your eye will be drawn to the sun side of the sky to look at them. And all they are is basically the kind of air being sunlit, but with clouds casting shadows. And this picture, my sister took this when she was in Mallorca, and she said, I thought you might like this picture. I was like, I love this picture because it perfectly demonstrates that crepuscular rays, all they are basically is just cloud shadows. And you can even see the baby shadow being cast by this little dude here. And that's all it is. It's lots of broken cloud, the sun rays passing through it, and it's a mixture of sunlit sky and cloud shadows. And that's all they are. Now, occasionally, you get them fanning out in all directions as well, and they can happen at any time of day, not just near sunrise or sunset when it's twilight. When you get really bright rays, like on this particular day last summer, the rays sometimes completely cross the sky and converge at the other side of the sky. Now, if we go back to that picture, you can see that all the rays are kind of fanning out from the sun in this tight kind of fan shape. And the same thing is happening on the opposite side of the sky. So it's kind of a bit trippy because there's no sun there. Obviously, these guys converge at the anti-solar point. And to actually see anti-crepuscular rays arching across the entire sky is quite unusual. Now, I did some panoramic pictures with my phone just to show you this is kind of more than 360 degrees, but the sun is here and these rays are arching over and converging on the anti-solar side. So that's there and there, because I did a really wide panorama and this is a slightly smaller one. And you can see that some of these rays are actually crossing the entire sky. It was one of those things that there just wasn't enough lens space to get all of this on. So I just kind of took a little video of it to try and show how bright these rays were and the fact that they crossed the entire sky and converged on the other side of the sky. So next time you see crepuscular rays that look really bright, it's definitely worth looking at the other side of the sky as well, because you can just faintly see them all fanning out here. And it was really bright again on the other side. They are fainter, obviously, because they've crossed the whole sky and they're not emanating from the sun. They're in the distance, and you can see that they kind of meet up on that side. So that was the 6th of August. Oh, gosh, that was 2 summers ago. Time's flying this year. So that was August 2018. Now, I was really fortunate to see a full set of anti-crepuscular rays on a flight back from Barcelona one year. This picture is another one that's one of my favorites, even though it was just taken with my Galaxy S5 mobile phone. These pictures show that these rays are coming from a spot of nothing. That is the anti-solar point. So to actually get a photograph that is showing the actual anti-solar point is really amazing. And to see these bright full sets of rays from the air like that, just extraordinary. Now, these rays, although they look like they're converging on the sun and the anti-solar point, they are actually parallel. And I understand this, but it still makes my brain hurt. The only thing you can liken it to is this square-shaped tunnel that has all these beams in it, lifted shamelessly from a Google search. But you know that this tunnel has not got smaller in the distance. It just looks like it has. Those ceiling fans here seem to, these beams look like they're converging in the distance. That is exactly what you're looking at with crepuscular rays and anti-crepuscular rays. The distances involved are so huge that basically they look like they're converging in both directions, and it just happens that they fan out over us because we're in the middle of it. And it's just amazing to me. Proof that they are in fact parallel came from the Apollo 9 crew, who took a photograph of crepuscular rays or cloud shadows going across the sky in a straight line. So this is proof from the Apollo era that these guys are going in a straight line. It's just the distances are so vast that they look like they're not. So yeah, definitely look out for them. I think they're amazing. I saw a good set the other day, and it's one of those things that just often goes unnoticed. Now, one last thing to talk about for now on the anti-solar side of the sky is something called the belt of Venus. Now, we very often at sunset or sunrise, our eye is drawn to the west at sunset because that's where all the colourful stuff's happening, the red sun and all of that stuff. Same in the east at sunrise. But very often you can get this band of dispersed red light over in the east at sunset or in the west at sunrise. Underneath that band, which is called Belt of Venus or Girdle of Venus because Venus apparently had a spangly belt that she used to wear. Beneath that red band, which is just caused by light scatter, basically, you get this grey band. Now the grey band gets bigger as the sun gets lower, and that grey band is the shadow of the Earth being cast onto the colourful sky beyond. And I actually time-lapsed this. We were on holiday in Lyme Regis a couple of years ago, and you can see that that gets longer, like taller and taller and taller. If you see this before sunrise, you will start off with this sky and see that in reverse. You'll see the red sky appearing and that grey band getting smaller and smaller and smaller. So that's the belt of Venus. So next time you are observing a sunset, make sure that you have a look in the east as well, because there are some interesting things going on. Likewise, if you're an early riser, unlike me, then look in the west at sunrise and you can see it as well. So I'm going to talk about kind of coronas and iridescent clouds now. And this is something else that I was completely unaware of until recently. Now, when you're looking at this around the sun, please do make sure you cover the sun with your hand, because it will hurt your eyes to stare directly at the sun. So very often coronas, which is what these things are called, are noticed around the moon more commonly than around the sun. And that's because it doesn't hurt our eyes as much to look at the moon. And what you see here is these concentric pastel colored bands, and then the whole pattern repeats and can carry on out. And I think the most ever recorded is a tertiary one. So you can get primary, secondary, and so on. And I actually think there were 4 or 5 times the repeat pattern. So this can carry on quite a distance if you've got conditions that are just right. And this is called a corona if you see the whole thing. Isolated patches like this are often referred to as iridescent clouds. It's pretty much assumed now that it's thought that they are one and the same thing, but you're just seeing fragments of them. This is one around the moon. You can see it's a little bit more easy on the eye, but the bands are often fainter because obviously the moon is reflected light. They are very, very beautiful. The colours are really gorgeous and pastel. I'm guilty of oversaturating my images myself sometimes, but it really winds me up when I see super oversaturated versions of these, because what makes these beautiful is the pastel colours for me. So what's going on here? This is not an ice thing. These are incredibly common. Anytime that you've got thin cloud, low level cloud, and the sun or the moon, then you can get them. Now these are water droplet effects. So these are clouds that are at a lower level and are consisted of water rather than ice crystals. And what causes these is diffraction. So there's no wavelength change going on here. This is just diffraction caused by these water droplets. The exact mechanism is still slightly unclear, but that's what's going on. The very center part is called the aureole, and then you get these concentric rings that kind of fan out from there. If you see this from in the air, it's called a glory. And I recently found out, I love hot air balloons, and I had an aspiration when I was a teenager to become a hot air balloon pilot. And there's a local historian to me whose talk I went to recently about Oxford Prison. And I noticed he'd written a book about hot air ballooning. Now there's a guy called James Sadler who was an Oxford pastry cook, and he was the most extraordinary guy ever, but his name had almost completely fallen out of history. If it hadn't been for the Jackson's Oxford Journal, nobody would be talking about him at all now. He invented balloons. He was one of the first aeronauts in the UK. He was one of the first people to do so many things in ballooning. Then he had a 25-year break where he went off and reinvented cannons and guns for the military. He was a chemist. He just did so many things. He was such a talented guy at so many things. I was reading this book recently because it's such an interesting book, and I came across this. During Commem Week on the 7th of July, 1810, James and John Sadler took off from Oxford. The halo about the shadow of the balloon was rich beyond description, the prismatic colours so vivid, distinct and complete. What they're describing there is a glory, and the glory is basically a corona, but as seen from the other side, if you will. But because it's around the sun and you are above the clouds, the sun is behind you, so it's kind of backscatter from seeing it from the ground, but you can sometimes see the shadow of whatever you're flying in the very center of it. I was really moved by this, and as yet I've got some of the references to read, But I think this is possibly the very earliest ever description of a glory as seen from the air. So I'm quite excited about this, and I want to go off and find the other early blueness accounts, because they wouldn't have known what this was. They obviously kept calling it halos, some called them rainbows. Even World War I pilots referred to these as rainbows, and they're clearly not. So they were not very well understood at all. But I wanted to commemorate this, so I actually drew a picture of this. I used some aerial photographs of Oxfordshire, and I found some pictures of glories from hot air balloons, and I used a photograph of the balloon that Sadler took off from Oxford from the book, and I made my own illustration of it, and I've sent it to the author to use in his talks, because I wanted to commemorate this, because I think it's a really important discovery that he could have been one, well, if he wasn't the first, he was certainly one of the first people to see this from the air. I'm not an illustrator from brain at all. I like doing astronomy stuff. I'm really not that good at this type of art, but I just wanted to throw that in there. I actually, the same flight that I saw the anti-crepuscular rays from, we actually saw this glory, which was covering a huge amount of the cloud base below us. On this occasion, we didn't get any aircraft shadow. I think we were just a bit too high. Sometimes you will get the aircraft shadow. And when you see pictures of glories, it's very interesting, because sometimes the nose of an aeroplane will be here in the center because it's the pilot that has seen it and taken the picture, whereas other times it'll be the middle of the aircraft here because it's one of the passengers that's taken a picture. So the glory will always center around the viewer. So if you ever see a photograph and you think, well, why is that plane here on that picture and here on this one? It's because a glory is another thing that is what is focused on your eyeballs and is different for everybody else on the plane. So these things are just amazing to me. I think it's really awesome. And you can just faintly see some of the anti-crepuscular rays fanning up there as well. I spent the whole of this flight with my face stuck to the window taking photographs, because there was interesting stuff going on all the time. Now, glories had been seen from the ground, from high ground before that, and this is something called a Brocken Spectre. Now, sometimes you will just see the glory. If you are on a hillside or mountain walking and there's a mist or a cloud below you and the sun is behind you, you can often see a glory. But if the conditions are right, you will also see this absolutely enormous long shadow of yourself. These were first discovered and first noted on Brocken, which is a mountain peak in Germany. So they're known as the Brocken Spectre, and they're almost certainly the basis for many legends about dark shadow watchers in mountains. And when you take into account, I think there are actually some myths around the mountains in Scotland as well, in the Highlands, the big grey men, I think it is, or the big grey man. And it's thought that that legend is also this phenomenon. When you're up on a mountainside or a hillside, you can get really weird wind effects and strange echoes and just very strange noises that can also be a kind of subhuman hearing frequency. And this type of noise is almost always at the base of any paranormal experience that humans have. So nearly all these legends of weird shadow men or giant men that walk around mountains are almost certainly to do with Brocken Spectres being seen and people not understanding. Now, I understand what a Brocken Spectre is. If I was faced with this, I would probably feel a little bit uneasy, to be fair. So it is something that is not new, but this is a glory, but seen from a mountainside, essentially. You can fake this if it's a foggy night, sorry. You can actually put your car headlights on and stand in front of your car and make a glory and a fog bow, all artificially. So Tom Lowe from Twitter let me use this picture to demonstrate that. So you can go out and play and do that yourself if it's a foggy night. Now, as I mentioned before, sometimes you will see just patches of cloud that have the colour like this. And this was just a few weeks ago. I was photographing aircraft at the time, and I just noticed that this whole area was just full of these colourful bands. And this is basically just iridescent clouds. Sometimes they do have the very definite lines and the stripes that the corona have. Other times they don't seem to. Like this one doesn't seem to have the same banding that a corona would have, but very definitely some beautiful cloud structure going on there. And that is what we're talking about with iridescent clouds. This can happen with aircraft vapor trails, because aircraft vapor is just water. this is an effect that I knew was possible. Several of my friends had photographed it. Almost at the beginning of lockdown, I managed to get a photograph of this for the first time, and I was so happy. These pictures went absolutely crazy on Twitter, mostly because the chemtrails brigade just lost their stuff completely and were kind of going mad about it. But basically, aircraft vapor is water vapor. Sometimes you see this effect within the actual exhaust water. Other times, like in this occasion, it's not coming from the engines only, it's actually condensing on the fuselage and the wings of the aircraft as well. So if you do have an aircraft in the right position, you can see the color spectrum within the vapor trails as well. Now I know this is possible. Every time I see a high level aircraft on a sunny day, I'm taking pictures of the condensation trails, but it's really beautiful. So that's the water vapor stuff done. So I'm going to move on to the sun side of the sky now and talk about pretty much, not all, but almost all of these atmospheric optical effects and what causes them and how to see them for yourself. So these are the names of these things, and I'm going to start in the middle and work my way out and just kind of do them in order. Then I'm going to move on to talk about clouds. Now, I've already talked about iridescent clouds. I'm going to talk about nacreous clouds and noctilucent clouds in a little while. But the clouds, it's usually cirrostratus clouds that have got the ice crystals required to form atmospheric optical effects and ice halos and stuff. Just to give you context, cirrus clouds are around about 6,000 meters above ground level. Commercial aircrafts go up to about 12 kilometers, nacreous clouds up at 25, and then noctilucent clouds are way up here at the edge of the mesosphere, up the edge of space, up at 80 kilometers. So cirrus clouds are the highest clouds, except for these supercell thunderclouds that go really high up above that. But just in general terms, cirrus are the highest clouds that we have. So they are icy. They are made up of ice crystals. This is an actual photograph of ice crystals sampled by Walter Tape. This was taken from his book. I have no idea how he did this, but this is showing that cirrostratus clouds are actually made up of hexagonal ice crystals with the odd pyramidal one in there as well. But you'll notice they're all different sizes. Some of them are flat plates, some of them are columnar, but it's the hexagonal ones that mostly cause the atmospheric optical effects. And depending on how these align with each other or how many of each type of crystal are visible will give rise to a particular kind of optical effect. Sometimes you'll have a mixture of all of the above, and that's when you get the multi-halo displays. So the common ones that are seen really regularly are the 22-degree halo here and upper tangent arcs and the circumzenithal arc. Now, tangent arcs are made by column crystals, the 22-degree halos and upper tangent arcs are made by columnar crystals. Sundogs and parhelix circles and circumzenithal arcs have got the flat plate crystals in. A parhelix circle needs both flat and columnar, so just shows you that there is a different source of ice crystals required for these different things. There are a number of criteria for halos to form. Just because there is cirrus cloud around doesn't mean you're guaranteed to get a halo or an arc. First of all, crystal quality is vitally important. It's like if you was doing your science experiment with a prism that had been kicked around and had divots out of it and inclusions in there that were stopping the light from passing through. So crystal quality is really vital, particularly for some of the rarer optical effects. Crystal size is also really important, and around about 0.05 millimeters is the optimum size. If they're too small, things can't form. If they're too big, things can't form either. So size is also important. And as I mentioned, the crystal alignment is important. 22-degree halos are the most common simply because you don't need any special alignment. It's just where the crystals are a big, massive jumble. So that's why you see them all the time. Whereas a parry arc needs a very specific alignment and good crystal quality. So the frequency of seeing these effects is down to all of these different things. Also, size and dispersion is important. 46-degree halo is all like just over double the distance away from the sun as a 22-degree halo, but it's 6 times fainter. So they very often go unnoticed because you just don't see them. They're a faint colorless arc in amongst a load of faint colorless clouds. So if you don't know what you're looking for, some of the rarer ones just aren't that easy to see. So first of all, I'm going to talk about 22-degree halos. This picture is around the sun. This one is around the moon. These are caused by tall columnar hexagonal crystals which have very poor alignment, and the sunlight is being refracted on the going into the crystal and out the other side, and the ones that are focused on your eyeball are the ones that are refracting the light by 22 degrees. It's also a fact that they cover 22 degrees of sky, hence their name 22-degree halo. And this is around the moon here, so you do see them day and night. I thought you could only get a lunar halo around a full moon, but pretty much any time after a half-lit moon, if the moon is more than half illuminated, then you can get a 22-degree halo. They are quite faint sometimes, but other times they're very, very bright, particularly in the winter. Now, 22-degree halos are way more common than rainbows, way more common than you might think. Actually, I read something in a book today that said in any one year, an avid observer may see 200 22-degree halos in a year. Compare that to 10 rainbows, and you can see that these guys are way, way more common than rainbows are. They're caused by refraction through poorly aligned crystals. The light's reflected by 22 degrees, as I say, and that forms this bright inner edge, and the red is always on the inside with all of these effects. Now, I've mentioned before that the sky on the inside of a rainbow was brighter than the outside. The opposite is true of a 22-degree halo. Very often the sky on the inside of the halo is darker, and that's because the light's being refracted away, and it obviously focuses at 22-degree mark. So the sky can look darker on the inside. Now, this is the crucial thing that makes them different from many other optical effects, is that irrespective of the height of the sun or the moon, the 22-degree halo stays the same size. It just doesn't change morphology at all. Sometimes the colors are more prominent than other times. You'll always get the red on the inside, the blue on the outside, as I said, but they are always exactly the same size. That's definitely not the case for everything. Now, quite often when I post a picture of a 22-degree halo, these things are quite big. If you put your arm out at arm's length and spread your fingers from your finger, put your thumb on the sun, your little finger is the outside of the halo. So although they're called little halos, they're actually quite big. And people quite often ask me, how big in real terms is the halo? And this is something that is really, really difficult to answer. And as I mentioned, you put your hand out at arm's length. Because of the geometry of our bodies, it means we can measure the sky. And a fully stretched finger and thumb there is 25 degrees, and a halo will fit just on the inside of that hand span. When people ask me how big a halo is, I answer 22 degrees. And that is not me being pedantic, it's me being real, because this is not a fixed object in space. It's not something you can fly to and see. It's literally ice crystals hovering in the atmosphere that are focusing on your eyes. And you could say, well, just use something else in the sky to give you a measurement in kilometers. So if we think about the moon, we know that the moon covers about 0.5 degrees of sky, and we know that the moon has a diameter of approximately 3,500 kilometers. So if we compare the lunar disk to the halo and do the maths, basically the halo is 150,000 kilometers across and in each direction. And that sounds huge, but then the sun is the same diameter as the moon. So if we compare it to the solar disk rather than the lunar disk, that sun is 1.4 million kilometers across, still covers the same amount of sky. So a halo would be 61 million kilometers across. So you can't give it an actual fixed distance in kilometers because it's not a physical object. And when you're looking at stuff on the sky, it's all relative to the background sky. So you have to do it in degrees because it's the only way that makes any sense. So yeah, if anyone asks you how big a 22-degree halo is, 22 degrees is the answer. Now, quite often when you have a 22-degree halo, you can notice a brighter patch at the top of it. Sometimes the brighter patch is funny shape like winged, or a sharp V like this. Sometimes it's a flat kind of concaved extending arc going out. This is an upper tangent arc, and you can also get lower tangent arcs. These are formed by the same kind of ice crystals, so they are very often seen in association with the halo. Sometimes they're not really noticed because they are pretty much at the same place as the halo is, but you just get a more colourful brightening effect at the top or the bottom of the halo, then chances are you're looking at an upper tangent arc. This is a lower tangent arc, photographed again from an aircraft, but this time on the way back from France. And I never know whether I want to be on the sun side or not the sun side of an aircraft, because there's interesting things going on in the sky in both times. And I've got other pictures of this flight to show you in a minute. But you can see that the lower tangent arc here is a really steep V shape. The crucial thing that changes the shape of them is the sun altitude. And this is another graphic that I made using Atmospheric Optics website. As the sun gets higher in the sky, the morphology of the upper and lower tangent arcs changes completely. And when the sun gets even higher than this, the lower tangent arc mimics this kind of wrapped around shape. So it's kind of sun-caved, we call it, because it's wrapping around the sun, but it's extending further outwards from the sun. And that is basically what's happening. It's all down to sun altitude differences. And that can give rise, when the sun is at the right altitude, to something called a circumscribed halo. Not as painful as it might seem. Basically what you have here, you can just see on the inner edge here that there is the 22-degree halo that is circular, but in addition to that, you can see an oval shape on the outer edges. Sometimes this oval shape comes down and has a weird kind of wonky bottom bit to it, but this is basically where the upper and lower tangent arcs have wrapped around in a sun-caved manner and met at the outside edges, and you can only get that when the sun is really high in the sky. So it needs to be kind of in the midday sort of period when you have a halo and you have the arc. One of the processes that you often use in atmospheric optics photography to try and see what you've got is a color subtraction process. So you kind of invert the image and subtract the color from it, and then you can kind of mess around with the levels. And what it essentially does is deletes anything colourful from your picture and leaves you with the grey arcs. And very often there are things visible in your picture with the colour subtraction and inversion that isn't that easy to see. So there is definitely a circumscribed halo here, but it's hard to see. It's much easier to see that there are two distinct arcs here when you look at the colour subtraction process. Same out here. So this is a circumscribed halo, and it is basically just an upper and lower tangent arc that are meeting at the outside edges. So height of summer for us in the UK to be able to see one of those. Another thing that is often associated with the halo are parhelia or sundogs, and this has brought me to a really interesting part of my talk. You know, until I got really into astronomy, I had no interest in history whatsoever, but looking at some of the history of the recording of these optical effects has been such a fascinating thing to look at. Now, I showed this picture briefly at the beginning. We're looking at refraction here. This is the light going in, getting refracted off one surface, getting slightly dispersed, and then refracting again and getting dispersed even more out of the two different parts of the ice crystal, and it gives you some color spectrum changes. You don't get the full spectrum, but you will definitely get the red on the inside, the blue on the outside, and generally a kind of whitish color in the middle. But sundogs are just so interesting because they can have very different morphologies depending on sun altitude and, excuse me, just depending on what type of cloud is visible. They can also only form when the sun is below a certain altitude. A lot of these optical effects were named a long time ago, like centuries ago. So they often have either Roman or Greek, Germanic names. I had somebody the other day ask him, why did I call my anticrepuscular rays a fancy name? Isn't it just cloud shadows? I was like, yes, they are just cloud shadows, but they're called anticrepuscular rays because that's literally their name. It's kind of like saying, why have you called yourself Mary? Why not random human? It's just mad to me that people would criticize the naming of an object that is its actual actual name. But anyway, parhelia, what I love about a lot of these effects is that the Greek Germanic names really make sense if you understand the language. So parhelia means beside the sun, and that's exactly where these things sit. They sit beside the sun. If you see one of them, it's a parhelion, two of them is parhelia, and the more common name is sundog. Now, in the 1st century AD, the playwright Seneca actually used the word parhelia in one of his plays. The earliest artistic representation is the Nuremberg Chronicle. Now, the Nuremberg Chronicle was the first book that was illustrated. It was Bible stories, but it actually had illustrated pictures in there. And it's really clear that sundogs and this atmospheric optical effects are being depicted here as the Holy Trinity. And throughout history, there have been references to this, and it's been used in that way for centuries, literally centuries. The most famous occurrence of sundogs and a halo was actually before the Battle of Mortimer's Cross during the War of the Roses. And this was in 1461. And Edward the Fourth, I think it was, Edward of York, he was due to march and go to battle, and the sun rose and it had sundogs either side, and there was a halo and possibly even some pillars as well. And it was described as 2 glorious suns, each a perfect sun. So 3 suns had risen. And the troops were terrified. They thought this was a sign that they were going to march off to their death. But Edward convinced them that it was a sign from God that they were going to march to victory, and it was all okay in the end. This had a powerful effect on Edward of York. He later became King Edward IV, and he actually changed his coat of arms to include the sun because this event was really important to him. And I have tried really hard to try and find how his coat of arms has changed over the years. It's very difficult to do that. I'm not an expert in coat of arms, but this is one of the ones that has suns on it when his earlier ones didn't. So I don't know for sure that this particular coat of arms is the one that he changed to include the suns, but there are 3 sun-like objects on this coat of arms. So I think this is the one that he changed. And it did make a really big impact on him. This was actually so important, it was reenacted in Shakespeare's Henry VI play, in Henry VI Part 3, Dazzle mine eyes, or do I see 3 suns? They're referring to sundogs. They are also called mock suns, and I think this is so romantic. The first description of them as being an actual atmospheric phenomenon dates back to 1533. We saw 3 suns as well as 2 rainbows. I feel this was no small miracle. Jacob Hutter was out looking for the Northwest Passage, I believe, and this was the first time it had been described as an actual atmospheric phenomena. And obviously they didn't understand this. They feel it was miraculous. They're still associating it with some deity or some sign or portent for something that's going to happen. So I think it's really awesome to see these quotes. Now, 2 years later in Stockholm, what's become known as the weather sun painting. You've got the sun here and all of these crazy different arts. I'd love to know what they saw because I can't liken most of these things to anything that I'm aware of. But this is depicting atmospheric optics, and it's the first painting of its kind to actually depict it as a weather phenomenon. And the king apparently of Stockholm was really not happy about this. He felt that this was some kind of test of loyalty to his reign. But that was the sky on the day of 1035, but the painting was actually done here. I've got the date wrong there. It was 1535, not 1035. But yeah, 2 years later is when this weather sun painting appeared, and it's really beautiful. And I have sketched atmospheric optics myself. It's really good fun. Now, somebody asked me to do some research for a blog a while ago on the origin of the word sundog, because that's the common name for it. The first recorded use of the word sundog was the diary of Naval Captain Luke Fox. Actually, it was him looking for the Northwest Passage, and he used the term in his writing, and it was obviously a commonly used term. He used it just in passing. He didn't invent it. So somebody else had obviously invented the term. So I don't know exactly when that was, but it became kind of commonplace. But it's thought that because sundogs are always following the sun as the sun rises or sets, they're kind of loyal dogs, like loyal dogs would be to a king or some ruler. pretty much every civilization has ancient writings that feature twin sons of sky gods. And also there's a lot of mythology around dogs as well. In Germanic mythology, Odin the sky dog had two loyal dogs, Jerry and Freki. And so this mythology around this has been there all the way through every civilization. And it could well be that they have seen sundogs and seen them as this kind of pictorial representation in the sky of the mythology that they've written about. And even going back down to cave paintings in Scandinavia depict twin figures that are associated with the sun. They're associated with fertility things and all sorts of twins being born. Pretty much the whole of history is filled with this kind of mythology. So there's a very good chance that it's connected to sundogs and atmospheric optics. So maybe these sundogs are Jerry and Freki, I don't know, but that's where we think it originated. And here is my sun cat posing next to a sundog. This is Coco, who likes to follow me out with my camera whenever I go out in the field behind. Now, as I mentioned before, sundogs can look very different. All of these pictures are of sundogs. Every one of them is a right side sundog. If you're looking at the left, the red colours would be going the other way, the whole thing would be reverse. Just the position of our garden means the sun is often behind a tree, so I nearly always see the right side ones and not the left. But they can change so much in morphology, and they're just so beautiful and interesting to photograph. This is one occasion where I was sick to my stomach that I was imaging with a wide angle lens, because there is definite colour separation in the vapour trails of this aircraft flying into the sundog. And I was imaging with the wide angle lens because I was doing a halo time lapse, and it's just makes me sick that this could have been such a phenomenal photograph, but never mind. And because we're near Kidlington Airport, we often get aircraft in that part of the sky, so it's really fun to photograph something else in association with sundogs. Now, I mentioned before that sundogs change with sun altitude. If you look at this picture here, when the sun is high but below 60 degrees, the ray deviation is increased. So sundogs are actually higher than the sun and sit outside of the halo. Now you can see there's a very definite gap here, but it's almost alongside, whereas on this picture here, the sun was even higher, and the sundog is actually higher than the sun and is also a long way outside the edge of the 22-degree halo. If the sun is higher than 60 degrees, sundogs can't form, and I'll explain why in a minute. So yeah, they change morphology, they change position, they change their distance from the sun, all very interesting stuff. This picture as well was quite a high sun, and you've got a fragment of a parhelic circle here, a massive gap here between the halo and the sundog. And yeah, so you can see that that one is also slightly higher than the sun. So sun altitude is really important. But this picture, the sundogs are actually in association with the halo. And on this one, you can see that it's tall and thin. So when the sun is lower, sundogs are pretty much alongside the sun at 22 degrees where the halo is. But when the sun gets low as well, you're then looking through more atmosphere, and this causes the ice crystals to appear to be wobbly. And that wobbling of the ice crystal causes the parhelia to become elongated and very tall. So they actually form a tall straight line alongside the sun. That is purely when the sun is very, very low in the sky. So sundogs are fascinating. They just always different, always changing. It's difficult to ever see two the same. You do also get parhelia in different locations as well. 120 degree parhelion would be 120 degrees away from the sun rather than 22 degrees. And if you didn't know what you was looking for, you would not know that that was anything other than a bit of cloud. It is just a white patch on a cloud, and that's pretty much it. 122 degree parhelion are caused by flat plate crystals, but they've got a very specific refraction path. The rays go in on the top flat plate, bounce off this plate, bounce off this plate, then come out again on this plate. So they're kind of going in at a slight angle, but going through the thin edge of the crystal. So that's the ray path. So you don't see them very often. I have photographed them a few times. This one is a little bit brighter. Excuse me. This picture, this particular sundog was actually brighter to the naked eye than the camera would depict here. So again, you wouldn't know that this was anything special if you didn't know that's what you was looking for. But it's very definitely 120 degrees from the sun. I measured it with my hands and it was exactly in line with the sun. So I know that it definitely was one. Sometimes if you were in the air, you can see these effects from the air. Now this is the sun reflected on a cloud, so it's called a subsun, and the parhelion alongside it is called a subparhelion. And very often if you are in the air and you can see the sun and sundogs or halos, you can see them reflected onto the cloud base as well. So always something interesting on aircraft. I always want the window seat and I always take thousands of photographs. Now I mentioned before that anything you see around the sun, you can get around the moon, and moon dogs are called paraseleni or parasaline if you're seeing one of them. They often are very much more muted in color, and that's because moonlight is obviously much fainter. Cameras do pick up more color than you see visually, but you can get them. I photographed them many times, usually in winter if I'm out photographing the moonrise. It's usually around a full moon that you would see them because they are so faint, and quite often you can get a corona at the same time if there's the right mix of clouds. So always look for those as well when the moon's around. Again, this is a brighter set of moon dogs that I had during sunrise. This is my house here. I was just at the end of the garden and absolutely beautiful. And the color subtraction process shows very clearly that there are these black smudges here. So this isn't an artifact, it is an actual effect. So yeah, all of these effects, if you get one around the sun, they're visible around the moon. One other thing to mention caused by exactly the same kind of crystal as sundogs is a sun pillar. And sometimes you can get a sun pillar visible long after the sun has set. Sometimes you can get one below the sun when it's still high enough. Very often they can extend really high up. And that is basically a sun pillar. And it's just, again, refracted light, but going off in a line vertically upwards. You can also get them going across as well, and I think that is what they saw before the Battle of Mortimer's Cross. I think they were seeing the cross shape of the two directions of sun pillar with the mock suns either side, and they saw that as a sign of the Holy Trinity, and that's why they were frightened. That's just speculation on my part, but that's what I think may have happened. Now, a pari-arc is probably the rarest of all of the optics that I'm talking about tonight, and these occur just above an upper tangent arc. And so often I see people post a picture of an upper tangent arc and say, oh, I've got a pari-arc, and very much no. They're higher up than that, and they're usually not very colourful like this, but they require very pure crystal quality. They also have a very specific ray path as well. There's a faint left side sundog here as well. But there's always a gap between the upper tangent or the top of the halo and where the pari-arc will sit. Now there's a complex ray path going on here for sun. Sometimes you get a sun cave like this one, sometimes the sun vex, which would be the V shape like I showed you earlier on. And that is determined by sun altitude. Pari-arcs change their morphology just as much as upper tangent arcs do, depending on how high the sun is. And the ray paths vary completely depending on sun altitude. And in order to get this ray path, you need a very pure crystal that's exactly the right size, which is why, and they all need to be orientated in a very specific way to allow this ray path. So that's why these guys are so rare. And I feel very fortunate that I've seen 3 of them now. And that's probably me done for a number of years because they really are very rare. So that would be sitting here where this is here. So we've done this bit. We're going to extend ourselves further out now and look at the stuff that you may see further away from the sun. Circumzenithal arcs have got the purest color separation of any atmospheric optics and rainbows and all of that kind of thing. They are utterly beautiful. They're one of my favorite optics to observe. And they're like an upside down rainbow. They arc upwards in the sky. And I've had people send pictures of them to me and they've corrected it to be the right way up because they think, oh, it's upside down, it looks wrong. And then they send it to me saying, do you know what this is? Well, if you've changed the orientation of it, how am I supposed to know what I'm looking at? Luckily, I recognized it was a circumzenithal arc and I said, it looks like that, but it's upside down. They said, oh yeah, I flipped it because it looked wrong. These things are supposed to be upside down. They're like an upside down smile in the sky. Now, I mentioned about the naming convention, circum meaning to go around something, zenithal meaning the point directly above your head. So these things are really high up. Most people do not walk around looking above their heads because you're looking where you're going. I do. I drive my mobility scooter off the curb all the time because I'm busy looking up at stuff. Circumzenithal arcs get missed an awful lot because they are so high above your head that you just don't see them. They're very often noticed by tennis players because they look up when they throw the ball up to serve. Interesting fact. Now, this is another optical effect that changes depending on sun altitude. When the sun is 5 degrees above the horizon, a circumzenithal arc will be at about 30 degrees above the horizon and be very faint, but a really huge arc. But as the sun gets higher in the sky, the arc gets smaller and it gets higher in the sky as well. And so this is from the zenith. So the brightest ones are when they're around about 22 degrees away from the zenith, and that usually is when the sun is about 27 degrees. And yeah, they change size and they change the curvature and they change their brightness depending on sun altitude. And again, once the sun is too high, you can't see them, they just kind of fade away. So just to give you some idea of where they sit, this is a 22-degree halo here. A circumzenithal arc is double the distance from the sun up here. If it forms a full circle, which it may sometimes do, that's not actually a circumzenithal arc. The second half of the circle is a Kern arc. They are extremely rare. I don't know anybody that has observed them. I just know that they're a thing because of textbooks. So if you ever do see this and it's associated with a full circle, you've got something extremely rare. And Kern arcs are caused by these weird like pyramids with the ends chopped off. I don't know what the name of that shape is, but they're generally known as a pyramidal display. So this is something more likely to be seen in a very cold area where you have ice crystals just in the air, like diamond dust if you go skiing and you've got all that glittery diamond dust stuff going on. And a Kern arc has some very interesting internal reflections to cause that arc to form. So some more pictures just to show you where they sit in relation to everything else. So if you've got the sun down here, top of the halo or the upper tangent arc would be there, and then go double that again and you've got the CZA. Quite hard to get it in one picture. You need a wide angle lens with the camera on its side and then you can kind of get it. They can be really bright, absolutely beautiful colors. They are so, so gorgeous. So definitely do try and look up a bit higher if conditions are causing halos. This is the one and only time I've photographed a circumzenithal arc around the moon. The moon was very bright, conditions were perfect. I had a lovely upper tangent arc and visually I was sure I could see something, was doubting myself, took a picture and there it was, full rainbow, very faint, but they do occur around the moon when conditions are right as well. These would be so often missed because you're just not looking at that part of the sky. Another thing that is up at that kind of height, as in double the distance again from the center of the halo, is a supralateral arc and a 46-degree halo, and they're often seen at the same time. Now down here is a picture of a circumzenithal arc. A supralateral arc actually butts up to that and curves around the sun, but is slightly flattened, so it's not a full circle. And this is another really bright supralateral. So that's why it's important if you see one of these things and take a picture, don't turn it the other way up because the supralateral arc bends that way, a CZA bends the other way. So they're two very different things. Something else you may see in association with that is a 46-degree halo. Now that will be circular, but as I mentioned before, they are 8 times fainter than the 22-degree halo. So they are often missed. They're very, very faint. There's just a hint of one there if you know what you're looking at. So I'm very fortunate again to have photographed supralateral arcs a few times and that they are relatively rare. Circumhorizon arcs is one that had eluded me for a very long time. These guys are caused by flat plate crystals again. They're not very often seen in the UK, and the reason being you need the sun to be above a pretty high altitude in order for them to form. And they're sometimes called fire rainbows, and that drives me nuts because they're neither a rainbow nor are they associated with fire. And I hate names that are that misleading. They're a circumhorizon arc, and again with the naming, circum meaning to draw a circle around something, and the arc. So if you had perfect conditions, this thing would basically form a full circular halo, a straight line as you're looking at it, but it would surround the entire horizon. So that's why it's called a circumhorizontal arc. They are right down here. So technically you would think that, yeah, from here to here is 22 degrees. So this is at 44 degrees thereabouts. So you would think that as long as the sun was 44 degrees above the horizon, you could see them. That is not the case. You need the sun to be more than 58 degrees. So if you live in an equatorial region, circumhorizon arcs are as common as the other things that we see around the sun. From the UK, there is a really small number of weeks where that's possible. So between the 15th of May and the 23rd of July, there is a chance you can see them, but only when the sun is at that altitude, and that only happens for between 30 minutes and a couple of hours during that time around local noon. So obviously that means our chances of seeing this are very limited from the UK, so I consider them to be quite rare. Now, as I said, they're very, very large and they are parallel to the horizon in a straight line. If you see something at that level below the halo and it's curving upwards, that would be an infralateral arc, the kind of other half of the superlateral, if you will, but these would be straight and parallel. And usually you only get fragments of them visible from the UK. This is an example of one. This had eluded me for years. Then when I was in Barcelona, there was the faintest hint of one, because in Barcelona, the sun is a lot higher, so there were more opportunities. And I saw one and I got a picture of one, but it was so faint that it needed so much imagination to know it was there. Then a couple of years ago, we were heading into London to go to a concert, and I think we were going to see the Foo Fighters, in fact. And on the way there, I noticed from in the car that there was a circumhorizon arc forming. It's broken up, but you can see that it's here. I mean, it's all the way out here as well. And it carried on all the way over here. And it's parallel to the horizon. It looks curved because of the lens on the wide angle on the phone camera. These would form lots of different spectral colors, but they have horizontal separation. So it would look like a flat rainbow, which is why it's important, if you see these things, to bear in mind where the sun is when you're seeing it. Because as I said earlier, it could be iridescent clouds, it could be a rainbow that you just seen the top of. But if it's on the same side of the sky as the sun, then it could well be one of these. So there are so many optical effects to look for. And once you know how to see them, there are just so many opportunities. This would have been incredible if the full arc had been visible, but it wasn't. But honestly, even though there are reflections from the inside of the windscreen, this was taken on the A40 doing 70 miles an hour with a phone. So I'm just really pleased that I got it at all, to be honest. I was really excited when I saw it. This is a better example of one from the Atmospheric Optics group. This was a guy who doesn't live in the UK and has far more opportunities to see it. And you can really see the straight banding there within that arc. Another optical effect that is quite rare and often missed purely because of how faint it can be is a parhelix circle. And this is sometimes associated with parhelion, as you'd expect, because the parhelix circle is a circular arc that, sorry, my cat has just jumped behind my thing trying to knock the light over. It's basically a circular arc that has the sundogs sitting with it. So you can see that it goes through the sun and out in this direction, and the sundogs actually sit on the line of this circle. Now, as I showed you before, sundogs change their position depending on sun altitude. So by definition, the parhelix circle also changes its position, and a parhelix circle is very different when the sun is above 60 degrees. So the size and the size, it doesn't change shape as much as size. It's always a circle, but it massively increases as the sun altitude decreases. So this is a picture that I took with a very, very wide angle lens converter. There's an upper tangent arc here. It's on its side. This was the top of the halo. And you can see this circle is huge. It goes all the way around this area. It was way bigger than the 22-degree halo. And there is a 120-degree parhelion here as well. And you very often get the 120-degree parhelia in association with this arc, as well as the 22-degree parhelion. So this is just a little graphic just showing you the effect of the sun. So when the sun is at a really high altitude, the parhelic circle is a ring actually within the inside of it. Then as the sun angle drops, the size of the circle gets bigger and bigger and bigger. And when the sun is setting, the parhelic circle would run the entire way around the horizon. They are white, so they can often be missed. Now, this is not my picture, but this is showing when the sun was at 80 degrees and the parhelic circle is inside the circle here. Now, because things can't form in here, it means sundogs aren't visible. Sundogs are only visible outside of the halo. So once this altitude changes enough to make this circle start going on the outside of the ring, that is when you start to see sundogs forming. So sun altitude is really important. When the sun's at 63 degrees, the parhelic circle is pretty much the same size as a 22-degree halo. So that's a good time to observe them. It's a good time to photograph them because the rings will actually fit within your field of view of your camera. This picture is taken from Ontario, and this is when the sun is much lower. You've got the 22-degree halo, you've got a sundog here, and then this huge ring going all the way around, and there's another little parhelion there as well, and there's a slight brightening here at 122 degrees. So these, quite often, I've actually seen 4 or 5 of these, and that was all within the first 2 summers of trying to find them. In each case, they were there for probably 3 or 4 minutes and then they'd gone. And if I didn't know what I was looking for, I would think it was a fragment of aircraft vapor trail, or I would think it was a bit of cloud or whatever. That it's very, very easy to miss them. And conditions in the UK usually mean that these things are very transient. They just appear for a short time and then they're gone. 22-degree halos can be visible all day for 3 days solid, but these other things tend to be really, they just come and go, basically, especially the rare ones. So you need to be kind of on the lookout. So that's most of those things that we've talked about here. Just that big picture again that was labeled, this was taken during hurricane when the conditions were perfect to get the multiple halo display. I've photographed pretty much all of these things, as I said, just not at the same time, which is extremely infuriating. But, you know, I always, every time there's anything cloud around, I've usually got my camera running just in case anything exciting happens. Just to give you an idea of relative frequencies of some of the halos, for every 100 halos that you get, you may only get 4 superlateral arcs or 4 parhelic circles. 122-degree parhelia or a pari-arc, you'll only get 1 for every 100 halos. So they are relatively rare, some of them. The other things are a bit more commonly associated, but the halos are definitely the most commonly seen. Now this video is one that I stole from YouTube, but in ski resorts you very often get these diamond dust displays. They are kind of the same principle. It's still refracted light from ice crystals. But as you can see here, you can see the glittering ice particles in the sky there. It's basically diamond dust in the air because it's really cold in these mountain regions. So you can end up getting these really beautiful displays. And here you've got a sub-parhelia, a sub-sun, a sub-sun pillar. All of this stuff can be reflected underneath if you're in a high area. So definitely keep a lookout for these things. You don't have to go to a ski resort to see them. You can get these things in the UK. You just need to keep your eyes peeled. And once you know what you're looking for, you realize they are relatively common. Now, I mentioned I was going to talk about nacreous clouds, so I'll quickly do that, and then noctilucent clouds. So nacreous clouds are a really high altitude cloud. They're sitting at about 25-30 kilometers high. So they're much, much, much higher than other clouds that we have. And these are usually visible for up to 2 hours before sunrise or after sunset, and usually only at high latitude and only ever during the winter months. Excuse me, conditions have to be just right to see these. This particular display, these pictures were by Mel Jeffrey. I wasn't well this day, and there'd been a really cold polar vortex had pushed really cold weather down to mid-latitudes. It's the only time I've ever been aware that nacreous clouds have been visible from the UK, and I missed it. We had cold weather for the next week, and I camped out sunrise and sunset for 4 solid days, didn't see it again. I missed it, and I genuinely cried. I was so frustrated that I'd missed it. But these pictures are really gorgeous, and they don't follow the same kind of pattern that coronas do. They don't have the concentric rings. They're sometimes called mother of pearl clouds, and they kind of seem to shimmer. And they're absolutely beautiful. Apparently once seen, they're never forgotten. The colors are more vivid. They're just beautiful visually compared to what you see visually with other types of displays. So yeah, one day hopefully I'll see them, but as you say, see them in isolation, they can look very similar to each other. So some things to bear in mind when you're trying to figure out which is which. If it's visible near the sun, it means it will be iridescent clouds. If it's after sunset or before sunrise, then the chances are it's nacreous clouds. Iridescence can happen any day, any year, any season. All you need is the sun and some clouds, whereas nacreous clouds will only be visible in winter and usually only at high latitudes unless circumstances have pushed a polar vortex down our way. The colours are generally more subdued when you look at iridescent clouds visually. Obviously, those colours are brighter in photographs, and particularly because everyone pushes the saturation up. But nacreous clouds are very vivid in colour without actually doing any of that. Iridescent clouds change form really quickly because that low level cloud with water droplets tend to be moving quite fast, whereas nacreous clouds change form really slowly. They're very, very high level, so the movements will have less, they'll move less noticeably in a given time, let's say. So basically, if you've seen some clouds and you think, oh, I don't know which it is, and it's an August day and the sun's out, the chances are what you've seen is not, in fact, nacreous, but more likely to be iridescent. So that brings me on to noctilucent clouds, which are a form of polar stratospheric cloud. And obviously you guys being up in Scotland probably have more displays of these than I get in Oxford. This year, I was so happy when I got this panoramic picture of the noctilucent clouds with Comet Neowise in shot as well. As soon as I found out Neowise was going to be visible in the north, I dreamt of getting that shot, and I did, and I cried again because astronomy just gets me like that, and I was very emotional that night, and it was a really beautiful display. Many of you will already know all about noctilucent clouds, but these are high-level clouds right up on the edge of space, and they remain illuminated after the sunset. Now, noctilucent translates as night shining, and if any of you have observed them, you'll know they do seem to shine against the background sky because the lower levels of atmosphere are in shadow at that time, whereas they're still being illuminated. So the temperature of the mesosphere has to be less than minus 123 degrees for ice to form there. It's very, very, very dry when you get that high up in the atmosphere. So you also do need a source of water. So that's why you don't necessarily get NLCs every night of the summer months. You do also need a nuclei to seed the formation of the ice crystals to form, and very often it's thought that that is meteor dust as it enters the upper atmosphere. So we don't know for sure. That's the most tried and trusted theory right now. Originally they thought it was related to volcanic ash, but who knows? We don't really understand noctilucent clouds that well as yet. The crucial thing about NLCs is they would be visible all day, except that the ice crystals that form them are so tiny. They're 0.1 microns, so that makes them too small for these clouds to be visible in bright daylight. So you need all the atmosphere to be in shadow first. Now, I showed you this picture at the beginning of these hexagonal ice crystals. The frame here, this is 0.1 millimeters, this line. So that gives you an idea of what size those cirrus cloud ice crystals are. When we're looking at noctilucent clouds, we're looking down here at 0.1 microns. So this was the ice crystals in cirrus clouds. Break that down by 10, take a tenth of it, break it down by 10, take another 1/10 of that, break it down by 10 again, and then take a 1/10 of that, and then you're down to 0.1 microns. Just to give you that in a probably easier to understand visual way, if you imagine that picture of those ice crystals that I just showed you, this hexagon here is about 0.1 millimeters across. This tiny dot here is the size of the ice crystal relative to the others that we see for ice halos. So they are so tiny. They're really, really, really tiny. And I just love the fact they're so small, and there must be literally billions and gazillions of them for a nice bright display to form. So these things are not visible in daylight, but once you need to be between 50 and 65 degree latitude. They're visible mid-May to mid-August, so we have just come out of the end of NLC season now. There have been reported sightings right through till September, but they're not very common. The sun has to be between 6 and 16 degrees below the horizon, and the noctilucent clouds are so high up on the edge of space that even then they remain illuminated by the sun. Now, they're always visible in the northern sky, and that's because they are polar stratospheric clouds, so they kind of accumulate around the North Pole. And we have NLC Daisy, which has got these, it's usually 3 days behind, but this is actual satellite pictures that are taken showing the accumulation. They're very, very difficult to forecast, or almost impossible to forecast, but it pretty much takes around 6 days for this entire Daisy to do one rotation. They are rotating. They have these weird arms of kind of accumulation of ice crystals. That's why it's called the Daisy, because it kind of looks like a flower, and you can just kind of keep track of it and find out when there's a chance that you may see them. They are just so beautiful. They're such a lovely time-lapse subject because they move in a very different way to tropospheric cloud. Now, tropospheric cloud would be in shadow at this point anyway, but this is super sped up footage here, and they just move in a very serene and beautiful way. And I'm obsessed with photographing them. I'm obsessed with time-lapsing them. This is normal cloud here, these stripes, and you can see that they're moving very differently. So this is normal cloud, this is noctilucent cloud, and you can see that it kind of falls in on itself. These things are running along and then kind of collapsing and forming weird kind of gravity patterns. It's just very interesting to watch. I've never seen 2 displays that look the same. They're just absolutely mesmerizing. They look like water ripples, and they really do seem to just glow. These are videos from last year and the year before. I did take loads this year as well. I mean, I could do an entire hour just showing you pictures of noctilucent clouds. I'm absolutely obsessed with them. This was the remains of a noctilucent cloud tornado, which I didn't know was a thing until 2 years ago. But 2 years ago, I had the most epic noctilucent cloud season. And they are just truly, truly gorgeous. I'll move on from that. So to finish my talk, I'm going to get onto the excitation part, and that is aurora. Now, you guys have probably had way more experience of aurora than I have in North Oxfordshire, but all of these pictures of aurora were taken from Oxfordshire. I've now had aurora on camera 13 times, I believe, since I moved here. There's been nothing for the last couple of years because the solar activity has just dropped so much that there's just nothing going on. But you can still get aurora just from a coronal hole. You don't necessarily need a big ejection or a flare from a sunspot. But it's an interesting thing to chase from such a weird latitude. It's not an easy thing to photograph. Of all these displays, that's what these 8 pictures here are the brightest ones that I photographed from here. Of those times, there were only 3 occasions where it was actually visible clearly to the naked eye. Mostly they were just showing up on camera, and they look very different to the naked eye. Now, as I mentioned before, we're talking about excitation here. What happens is solar wind comes along, these charged particles from the sun get into our atmosphere. They energize the molecules in the air, and their electrons move up into the excited state, and then when they drop down, they emit photons. And that really the color of photons that are emitted is determined by, first of all, how energetic and excited state it gets to, but also which molecules are actually being excited. So it could be oxygen, it could be nitrogen, they both give you different colors, but equally nitrogen and oxygen can give you two different colors depending on the excitation state of them. So it's quite interesting. You guys will already know this, but the solar wind powering towards Earth, we are very fortunate that we have a magnetic field that kind of protects us, so it sort of deflects it off around there. The magnetic field looks like a giant insect which extends right out on the opposite side from the sun. When those charged particles hit, they kind of get channeled down towards the polar regions, and that's where they then excite the air molecules and cause the colourful aurora to happen. It's basically the air glowing, if you will. And that is why the aurora is commonly around the pole, and it's almost every day there is aurora around the North Pole or the South Pole. It just, how far south that auroral oval gets pushed is really determined by how energetic the solar wind actually is. Now, to get aurora, obviously you need energetic solar wind, but to get it at mid-latitude, you need very energetic solar wind, and that can often come from coronal holes. And coronal holes are just where the magnetic field has been disrupted, so the charged particles can come out more aggressively. And it's really interesting, if you look at coronal holes, they have been responsible for more of the aurora displays I've seen than Earth-directed coronal mass ejections have. Coronal mass ejections are again associated with magnetic fields. Because the sun has a differential rotation on the equator versus the poles, those magnetic field lines that would start off quite uniform like we have on Earth get twisted up. And also there are magnetic field lines associated with sunspots. They have polarity, all this twisting goes on, and eventually they just snap, and that ejects all of the material out into space. And if that is Earth directed, then it can give rise to really nice bright auroral displays. Now, there are several criteria in order to get aurora from mid-latitude. First of all, you need the correct polarity. If the solar wind gets here, it gets channeled to the South Pole, then the Northern Hemisphere doesn't get any aurora. And there's no way of really knowing whether it's going to go one way or the other. It's a really complex thing. And if you look at the aurora apps, you're looking at the BZ, the polarity. You want a negative polarity in order to push the aurora to the north, or well, the activity to the Northern Hemisphere, I should say. Now, during the summer and winter months, particles don't interact as well as they do during spring and autumn. And I find it interesting, people talk so much about aurora season. The brightest aurora that I've ever seen was on Midsummer's Night. So, and it was from Oxfordshire. And you just, all of those things just shouldn't add up. I should not be able to see that at that time of year. You guys further north couldn't get that display because you don't get enough darkness at that time of year. So I was really fortunate to have got that one. It was another occasion that I cried as well because astronomy. So yeah, during the spring and autumn months, you do get a better interaction. I don't know why that is. I do have a book on this, which I haven't read yet, so I hopefully will know that soon. You also need clear skies and no interference from the moon. And as astronomers, how often do we know that clear skies often don't coincide without a full moon being there? So that has to work in your favor. You also need dark skies. Now, as I mentioned, where I am, I have the advantage that we don't get astronomical darkness in June and July, but we do get darkness. So on Midsummer's Night, I was able to get an hour and a half of aurora, whereas anybody north of Birmingham couldn't see it at all. So it pays to be further south, very, very few occasions. Further north is definitely better. Now, there are several notification apps. The only thing you can predict about aurora is its unpredictability. Very, very difficult to predict. Now, I have very often had people say, oh, you're so lucky you got aurora on this night or that night. Now that I know it's possible to photograph aurora from here, the minute there's a hint of the KP getting above 5, I will go and sit in a field. We have a field near us with a really good northern horizon, and I will go and sit in that field and take 1,000 photographs, getting very, very cold, watching absolutely nothing happen. The reason I do that is because if we do get a spike of activity, it very often only happens for 15 minutes, then it drops off again. So if you're not there and you're waiting for social media to tell you that it's happening, there's a good chance you're going to miss it. Now, further north in Scotland, if you've got good activity, the chances are that you have a bit more of a consistent display during the night. But certainly from here, I need to be there just in case. So I've genuinely spent hundreds of hours sat in a field getting nothing. So I get a bit offended when people say you was lucky to get this, that, the other, because I spend a lot of time trying to capture these things and being in the right place at the right time. Now, you do need to get away from city lights to see this, and you need a good northern horizon. Now, I'm very lucky that a mile outside our village is a field that is at the top of a steep slope that looks down on the northern horizon. So I'm actually higher up, so it means I get a really good view of the aurora from there. Very important that your eyes are dark adapted, or else you're really not going to see it visually because it's often very faint. And don't expect bright green and purple fireworks. On a daily basis, we're bombarded by heavily saturated aurora photographs. Yes, it's true, cameras are more prone to picking up colors, they're more sensitive to those colors, but people, and I'm guilty of enhancing the color in my images myself because it looks pretty, but some of them you see of just like day glow, violent kind of green color that looks like a highlighter, and it just isn't that color. When you see it visually, it just isn't like that. So visually, do not expect that sort of color. Now, this was the brightest aurora display that we had from here, and this is kind of what it looked like. I tried to process this picture to reflect what we were seeing. This is a band of cloud. Banbury in the distance, there is light pollution from Banbury, but there was a green arc that was visible over that. This whole arch was visible for ages. These pillars were actually grey to look at, but they were really clearly visible, reaching all the way up to about 50 degrees of sky, and they were extending out way beyond the field of view of my camera. They were dancing back and forth. It really was spectacular, but it did not look purple and red. My camera was really picked up the colours in that. This is another bright display that we had. There's Banbury here, but there is definitely green here as well. After many, many hours at that field, I've learned how to decipher the difference between light pollution in Banbury and what is aurora. Now, this night, the green glow was visible all night long, and that was very definitely green to the naked eye, but these pillars were barely visible at all, and they certainly were not purple. So your camera will pick up activity that your eyes can't see. So if you get an aurora alert, it's really worth just pointing your camera north. I tend to do around ISO 800 for 10 to 15 seconds if there's a faint display, because you need a long exposure to detect it. However, if you've got a very active display, or you've gone somewhere like Iceland to photograph aurora, then basically you need to not do 10-second shots. That's where I went wrong with my bright aurora display. Aurora is not a static object, so if it's moving and you do a 15-second shot, your pillars become smears rather than crisp tall pillars. So bear that in mind. If it's a very active display, then definitely not as long a shutter time. And then just shoot on continuous, because that will then show up any movement of the pillars. And the pillars do move around, and quite often it's hard to tell if what you're looking at is light pollution or something else, or just general haze. If you take a load of pictures and then just scroll through them, you will be able to see whether what you've got is actually aurora. And that has been what has saved me many, many times. So this was 2014, the first time I photographed aurora from Oxfordshire, when I didn't even know it was possible. I had no idea how to shoot a time-lapse video, so it's pretty grim, but this was one heck of a bright display that was clearly visible naked eye. This display was during a full moon taken from a window, and there's just a slight ripple here. Visually, you couldn't see it. On a single shot, you couldn't see it, but on a time-lapse, you can. This would have been epic had it not been so cloudy. We get a lot of foggy. We get a lot of fog here, so we do tend to miss those things. This was the second time I'd actually photographed aurora from Oxfordshire, and there was definitely two different colours of red and purple here, the green down here. Another night would have been a great display had it not been for the clouds, but sometimes the tropospheric cloud adds another dimension. It's frustrating though when you get cloud. And it's just these little ripples that may just happen for 15-20 minutes and then they're gone. So you already need to be in position to capture them. So this is the really bright one. I still can't believe when I see this video that it was taken from North Oxfordshire. It really was something quite spectacular to see. And I don't know if I will ever see a display quite like that from Oxfordshire again as long as I live. Hopefully I will, but now I know it's possible. I spend a lot of my time sat in fields and living in hope. So that's everything covered. I hope that you now see clouds in a slightly different light than you did at the beginning of the talk. There are some very beautiful effects to look at. Once again, please cover the sun with something if you are going to try and let me just unmute everybody because I think someone has a question. Was it Alt and A? Alt M.
Alt M.
Thank you. I've done Alt M. Is everybody unmuted now?
Yes.
Excellent. Okay. Fab. So yeah, I hope you guys have enjoyed that and you view clouds in a different way. Further reading, just very quickly, atmospheric-optics.co.uk is excellent resource. This book is fantastic. It's turgid, it's quite tough to read, but it's really, really good. It's very, very informative and not one you can read cover to cover, but worth dipping into. And Isaac Newton's book obviously is a seminal work on optics in terms of light. So thank you very much. Someone just put up their hand. If you're unmuted, if someone had a question, that's great. I'm just going to stop the screen share.
I've never looked at
No, it's not a question. It's just some things that my wife and I have seen over the years.
Right.
Many moons ago, I saw a fourth rainbow.
Oh, did you?
By the time I got the camera out, you can guess what happened. The fourth one had disappeared. I took a picture. The third one was quite clear. I took a picture, but the third one didn't show up. But that evening on our local TV news, the weatherman at the time, perhaps Bob might remember, was Tony Target. Remember Tony Target, Bob?
No.
No. Anyway, he actually did. Someone did send a picture in of the fourth rainbow, and Tony did point out that these actually the number of rainbows can go on for infinity.
Amazing.
The other thing was something I didn't know what it was called. I got a photograph here in my iPad somewhere of something I saw from an airplane. This thing, and you called it a subparhelion.
Subparhelion,
So,
yeah.
I didn't know what that was, but I do now. We followed it for several miles from the airplane.
It's amazing, isn't it?
Manage to get a picture of it. The other thing was, I think it was 1988. You might be able to find it on Google. It was the biggest aurora display seen in this part, Gloucestershire, on record. In fact, it was actually seen all the way down to the Mediterranean. I got all the neighbours out in the lane to have a look at all the different colours. It was lit up all around. And that's the reason why I wouldn't waste money going on one of these airplane flights out over the North Sea or somewhere to try and see them. I've seen probably what's going to be the best display I'll ever see. I think it's 1988. And then I think 1990, there might have been another good display from Gloucestershire. Absolutely incredible. So bright, the colours, every colour you can think of.
Yeah, it's amazing. I mean, I've been on 2 aurora flights, and one of the ones that Pete Lawrence is involved with. The first one that I went on was the one of only 2 flights that they'd ever done that didn't see anything. It's so frustrating. I still enjoyed it because they turn all the lights off and it was just lovely. But yeah, the other time it was kind of faint, and I just stopped trying to take pictures of it. I just wanted to watch because it was, you know, I knew it'd be quite special being the first time I'd seen it. But now I know that it's possible to do from mid-latitude. I spend a lot of my time sat in that field. It's quite crazy.
Went on one of these cruises up the coast of Norway to see it. I'm not sure how much it cost, £1,000. You didn't see anything. It rained nearly all the time.
Oh gosh, that's what worries me about going to
Yeah.
Norway or Iceland, is they get a lot of cloud.
Yeah. Yeah.
I
Yes,
forgot to mention, when photographing rainbows, because rainbows are polarized, a polarizing filter will help you to see or photograph them better. But the ice halo stuff, the refracted light, is not polarized, so a polarizing filter won't do anything. It's a question that I get asked quite a lot, and I forgot to mention it in the talk. So,
David Ramshaw at Border Astronomical Society. One of our founder member, David Pettit, unfortunately he died 2 or 3 years ago. He was a fellow of the Royal Astronomical Society, and the reason for that was that he designed a magnetometer which had in his back garden, and it became quite well used at the time. I think it's in the late 70s, and I remember he used to telephone us when his magnetometer, it had a chart recorder, and it indicated when there was a lot of activity. And I remember he took pictures then, I think it was late 70s. The best ones that I had just from his back garden in the middle of Carlisle, as well as from further along on the Solway. And it was said at that time that these aurora could be seen down in Cornwall. And he actually had pictures of looking directly up at the centre of the.
Yeah, I think the ones from 1988 were seen all the way down to the Mediterranean.
yeah, I was going to say they were seen in France, weren't they?
1988, with the society's been going from the early 70s, I can't really recall what year it was, but we've got a couple of pictures on the website from that time.
Yeah, there were some amazing displays.
In one of your pictures, you've got, like you said, it was like the columns, and then it was the green at the bottom. I saw exactly that in Shetland. It was in November. Yeah, it's like the exact same as your photograph. It was long white, like columns, pillars. And my son-in-law, because he comes from Shetland, he says, you might not think that's the aurora, but it was. And then we went away, and then we came back out later on, and we saw the green running along.
Wow.
Fantastic.
It's so special, isn't it?
It was. Couldn't believe it.
I was in bed.
I messaged my husband and I said, guess what I've seen? Oh, the aurora, yeah, the Northern Lights.
Yeah, you need to be away from light pollution and have a good view north. And I lived in Lancashire for most of my life, and I never once saw aurora because I was south of Preston and there's so much light pollution. I moved to Oxfordshire and I was like, I'm never going to see it now. And then 13 times I've photographed it. So, and now we're in solar minimum. So now the activity's picking up again. Hopefully the aurora will pick up again. Fingers crossed.
I was in bed and breakfast in the north, some bed and breakfast place on the north coast of Scotland about 20 years ago. And the lady said, I've had my bed and breakfast going for 2 years. I've never seen any aurora.
Yeah.
Oh, wow.
I went to Iceland last year with my wife for 5 days with a specific intention to photograph aurora, and it was cloudy just about every day. We had no chance whatsoever. And that was in the spring. You mentioned sun pillars.
Yeah.
You mentioned seeing them in the evening after sunset. I remember taking my wife to work a few years ago and seeing a sun pillar in the morning.
Yeah, you can get them sunrise or sunset.
It was it was quite obvious what it was. You know, it was,
Yeah, you get moon pillars as well. I didn't put a picture in the talk. This talk keeps growing. I keep trying to get it back down to an hour and I just can't, because every time I read something else, I'm like, oh, I've got to include that because it's just so interesting. And yeah, moon pillars are beautiful because they're white, and I love moonlight anyway. It's just so pretty. So.
Because I photographed a sun pillar a good few years back, you know, and I didn't realise what it was, and it was really bright. And I just took a quick snapshot of it, and I showed it to some of them at the Astronomical Society meeting, and it was somebody there that told me it was a sun pillar, you know. And I've never seen one since. So, but I mean, it was really, really bright. And last year, I saw, I think it was last year, time moves that fast, it was a double rainbow, but it was enormous, and it was, both rainbows were really, really bright, you know, and they lasted for, maybe 15, 20 minutes in the sky. But I didn't have any to photograph them, and I was in my car at the time. My pal was driving, and I just stared out the window at these beautiful rainbows, and he's going, "It's just a rainbow," and I'm going, "No, no." You know, I couldn't get over it. It was just so bright. You know, the colours were so vivid.
They are so beautiful.
Oh, I says, every time I see a rainbow, I'm like a 5-year-old child.
Well, I love the fact that nobody can see your rainbow. It's your personal rainbow, because it's the light particles focusing on your eye. So your halo and your rainbow are unique to you. So there's no guarantee that the person standing next to you has got the same raindrops. It's mental.
Because a way back, it must have been about 2000, 2001, something like that. I saw one of those iridescent clouds.
Oh, yeah.
And it was just because my front of the house faces west. So it was the winter time. And I was waiting for my sister coming in just to see me briefly before she went up to hers. And I saw this in the sky, you know, and I'm thinking, hang is it? Because it had snowed earlier, you know, and I'm thinking, hang is that? I didn't have a clue what it was. And she came in, and I'm pointing it out to her, and she's going, "Oh, that's beautiful." It was really bright, and it was quite a fair size as well, you know. And it lasted for quite a wee while, because I was standing at the window for about 15 minutes, and I'm like, "What the hang is that?" But it was
I knew what a sundog was before I'd ever seen one, but I don't know how I knew what it was. I don't remember learning about it, but I knew about sundogs and halos, and that was it. And then I moved to Oxfordshire and started diving into it a bit more, and it's just such a fascinating subject. And yeah, I mean, there's way more things you can see than what I've covered tonight. I could talk for an hour just about rainbows. I mean, it's just so scientific and so in depth and so utterly fascinating, and stuff that I'd never been aware of until I was like 5 years ago.
I have tried to photograph them before, but they never come out the same in the camera as what you see them in reality, you know. And so I don't know whether I'm photographing them at the wrong F settings or what, you know. So what F setting and ISO would you put it at then?
What, for a rainbow or for the other optics? If I'm doing rainbows, I generally do it with my phone, to be honest, and just pull the exposure thing down, because you can do the panoramic thing with your phone and fit it all in. With halos and sundogs and stuff, I tend to put the f-stop up at 22 to cut out most of the sunlight, and then ISO 100, and then around about 1/2000th of a second, because you're pointing straight at the sun. And if you ever are doing a time lapse, don't put your camera on a tracking mount, because each time the shutter fires, it may only be a small fraction of a second, but if it's tracking and the sun's hitting the same part of the sensor 1,000 times, it's going to destroy your camera. So I always let the halo move, and I have the f-stop right down, really fast shutter speed, lowest ISO, and then I just post-process everything before the time lapse to just make sure it looks good. So yeah, I stop it right down to just make sure there's no camera damage, and I always leave a 15-second gap between pictures, and I don't have it tracking, so the sun is then moving across the sensor for each shot. So quite important that you protect your camera. And your eyes as well. It's really important to put your hand up and just cover the sun.
Because I was really annoyed last year when I didn't have my phone with us, you know, because we were in the car and there was nowhere to stop. But with that big double rainbow, I wanted to photograph it, and I'm going, no, I can't. Oh. And I thought, time I get home, it'll have gone.
Well, the polarizing filter will help with rainbow photography for sure.
Aye.
It makes it way more vivid.
Aye. Oh, I mean, these were really so bright. I just was in
You didn't need a filter. Yeah, they are fascinating.
Aye. Is there any other questions?
No.
All
Sorry,
right.
I've kept you really late again. I did this last month.
So I'd like to thank Mary in the usual way.
Thank you.
Okay.
Excellent talk. It was.
Right. So
Yeah.
thank you both,
Thank
Eddie and Mary, for your excellent talks. And I mean, we really learned a lot from both talks about the astronomers that discovered, you know, Neptune and that, and plus all about these atmospheric optics that we sometimes see, although I've never seen an aurora. But some of these optics that you don't know very much about them, you know, they're just fascinating, beautiful objects in the sky. That when you hear all about the science behind them, I mean, it's fascinating, you know.
Yeah, just millions of tiny ice crystals that are focusing light on your eyes. It's just wonderful. And we have a lot of clouds in the UK, so embrace it and just learn about it.
I know I like doing like sunset pictures or sky shots and that, you know.
I fill up a lot of memory cards.
Well, in Scotland and Forth, we have quite a lot of cloud and quite a lot of rain. So we only have one day of summer.
Really enjoyed it, Mary. Thank you.
Thank you.
Hey, thank you again.
Thanks again. Thanks again.
Thank you.
Good night. Thank you.
Good night.
Thanks.
Okay,
Bye,
thank-
everyone.
Right.
Thank you.
I'm going to drop off. I'll see you next time. Bye.
Okay,
Thank you.
bye.
Night.